we are diving into the architecture that revolutionized natural language processing, the transformer. Before we look at the code, we need to understand the attention is all you need paper and why it moved us away from traditional recurrent neural networks.
Translation, it's done with a transformer. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about transformer neural networks and they're going to be clearly explained. Transformers are more fun when you build them in the cloud with lightning. Bam. Right now, people are going bonkers about something called ChatGPT. For example, our friend, StatSquatch, might type something into ChatGPT like, "Write an awesome song in the style of StatQuest." Translation, it's done with a transformer. Anyway, there's a lot to be said about how ChatGPT works, but fundamentally, it is based on something called a transformer. So, in this StatQuest, we're going to show you how a transformer works one step at a time. Specifically, we're going to focus on how a transformer neural network can translate a simple English sentence, "Let's go," into Spanish, "Vamos." Now, since a transformer is a type of neural network, and neural networks usually only have numbers for input values, the first thing we need to do is find a way to turn the input and output words into numbers. There are a lot of ways to convert words into numbers, but for neural networks, one of the most commonly used methods is called word embedding. The main idea of word embedding is to use a relatively simple neural network that has one input for every word and symbol in the vocabulary that you want to use. In this case, we have a super simple vocabulary that allows us to input short phrases like "let's go" and "to go." And we have an input for this symbol, EOS, which stands for end of sentence or end of sequence. Because the vocabulary can be a mix of words, word fragments, and symbols, we call each input a token. The inputs are then connected to something called an activation function, and in this example, we have two activation functions. And each connection multiplies the input value by something called a weight. Hey Josh, where do these numbers come from? Great question, Squatch, and we'll answer it in just a bit. For now, let's just see how we convert the word "let's" into numbers. First, we put a 1 into the input for "let's," and then put zeros into all of the other inputs. Now we multiply the inputs by their weights on the connections to the activation functions. For example, the input for "let's" is 1.
The heart of the transformer is self-attention. This mechanism allows the model to weigh the importance of different words in a sentence relative to one another, regardless of their distance. Let's look at the mathematical intuition behind queries, keys, and values.
Over the last 2 or 3 years, the AI and machine learning community have been building bigger and bigger models that are doing more and more impressive things. Nowhere is this more apparent than in natural language processing, where we've seen really impressive models like the GPT-3. You can refer back to my previous video to learn a little bit more about GPT-3. We saw a couple of the demos, the examples that the model was able to do, build a website, or learn how to build websites, I guess, based on a few examples, or learn how to retrieve information or data from just the data it was pre-trained. This is a quote that I found interesting by David Chalmers, a scientist focused on philosophy of mind, saying that GPT-3 is instantly one of the most interesting and important AI systems ever produced. I agree with this sentiment. I find them fascinating. Now, the transformer was first proposed in this paper. It's one of the technologies that are underlying a lot of this rapid progress in natural language processing and in AI and machine learning as a whole. So this 2017 paper, I believe, introduced the model came out of Google and University of Toronto researchers. A transformer basically is a type of machine learning model. It's an architecture of neural networks. Since then, variants of the transformer, namely a variant called BERT that builds on top of the transformer, has grown to dominate the models of natural language processing in various tasks. These are some leaderboards that researchers use to rank and rate models, and the top scoring models from this snapshot are all based on BERT, which is based on the transformer. Google has rolled out BERT and transformer-based models to Google Search. They've been using them to empower Google Search, and they call it one of the biggest leaps forward in the history of search. So this is important stuff. Now, over the last 2 weeks, we have developments that extend the value of transformers beyond just natural language processing. And so this is a conversation between two senior AI and ML researchers. Oriol is in DeepMind, and Ilya is the head scientist in OpenAI. And based on this paper on vision transformers that applied transformers to computer vision, and Oriol thinks that it's farewell to convolutions. And so deep learning in computer vision has been dominated by convolutional neural networks that have been producing the best deep learning models in computer vision. But right now, starting from a few weeks ago,
one problem with attention is that it doesn't naturally understand word order. To fix this, researchers introduced positional encoding. This adds a unique signal to each word embedding so the model knows where each word sits in the sequence.
In this video, we'll study the encoder architecture. An example of a popular encoder-only architecture is BERT, which is the most popular model of its kind. Let's first start by understanding how it works. We'll use a small example using 3 words. We use these as inputs and pass them through the encoder. We retrieve a numerical representation of each word. Here, for example, the encoder converts those 3 words "Welcome to NYC" in these 3 sequences of numbers. The encoder outputs exactly 1 sequence of numbers per input word. This numerical representation can also be called a feature vector or a feature tensor. Let's dive in this representation. It contains 1 vector per word that was passed through the encoder. Each of these vectors is a numerical representation of the word in question. The dimension of that vector is defined by the architecture of the model. For the base BERT model, it is 768. These representations contain the value of a word, but contextualized. For example, the vector attributed to the word "to" isn't the representation of only the "to" word. It also takes into account the words around it, which we call the context. As in, it looks to the left context, the words on the left of the one we're studying, here the word "welcome," and the context on the right, here the word "NYC," and it outputs a value for the word given its context. It is therefore a contextualized value. One could say that the vector of 768 values holds the meaning of the word within the text. It does this thanks to the self-attention mechanism. The self-attention mechanism relates to different positions or different words in a single sequence in order to compute a representation of that sequence. As we've seen before, this means that the resulting representation of a word has been affected by other words in the sequence. We won't dive into the specifics here, but we'll offer some further readings if you want to get a better understanding at what happens under the hood. So when should one use an encoder? Encoders can be used as standalone models in a wide variety of tasks. For example, BERT, arguably the most famous transformer model, is a standalone encoder model, and at the time of release, it be the state-of-the-art in many sequence classification tasks, question answering tasks, and masked language modeling, to only cite a few. The idea is that encoders are very powerful at extracting vectors that carry meaningful information about a sequence. This vector can then be handled down the road by additional neurons to make sense of them.
Now that we have the components, let's look at how they are stacked. We'll explore multi-head attention and the architectural differences between the encoder which reads the input and the decoder which generates the output.
In the last chapter, you and I started to step through the internal workings of a transformer. This is one of the key pieces of technology inside large language models and a lot of other tools in the modern wave of AI. It first hit the scene in a now famous 2017 paper called Attention is All You Need, and in this chapter, you and I will dig into what this attention mechanism is, visualizing how it processes data. As a quick recap, here's the important context I want you to have in mind. The goal of the model that you and I are studying is to take in a piece of text and predict what word comes next. The input text is broken up into little pieces that we call tokens, and these are very often words or pieces of words. But just to make the examples in this video easier for you and me to think about, let's simplify by pretending that tokens are always just words. The first step in a transformer is to associate each token with a high-dimensional vector, what we call its embedding. Now, the most important idea I want you to have in mind is how directions in this high-dimensional space of all possible embeddings can correspond with semantic meaning. In the last chapter, we saw an example for how direction can correspond to gender, in the sense that adding a certain step in this space can take you from the embedding of a masculine noun to the embedding of the corresponding feminine noun. That's just one example. You could imagine how many other directions in this high-dimensional space could correspond to numerous other aspects of a word's meaning. The aim of a transformer is to progressively adjust these embeddings so that they don't merely encode an individual word, but instead they bake in some much richer contextual meaning. I should say up front that a lot of people find the attention mechanism, this key piece in a transformer, very confusing, so don't worry if it takes some time for things to sink in. I think that before we dive into the computational details and all the matrix multiplications, it's worth thinking about a couple examples for the kind of behavior that we want attention to enable. Consider the phrases American shrew mole, 1 mole of carbon dioxide, and take a biopsy of the mole. You and I know that the word mole has different meanings in each one of these, based on the context. But after the first step of a transformer, the one that breaks up the text and associates each token with a vector, the vector that's associated with mole would be the same in all three of these cases, because this initial token embedding is effectively a lookup table with no reference to the context. It's only in the next step of the transformer that the surrounding embeddings have the chance to pass information into this one. The picture you might have in mind is that there are multiple distinct directions in this embedding space, encoding the multiple distinct meanings of the word mole, and that a well-trained attention block calculates what you need to add to the generic and move it to one of these more specific directions, as a function of the context. To take another example, consider the embedding of the word tower. This is presumably some very generic, non-specific direction in this.
Theory is great, but seeing a transformer built from scratch is the best way to master it. We'll now look at a practical implementation to see how these tensors actually flow through the network layers.
Welcome to this lecture on using large language models the way Andrej Karpathy does. Karpathy, former AI director at Tesla and a founding member of OpenAI, made a remark that stopped the AI community in its tracks. He said that LLMs represent an entirely new kind of computer, a stochastic, text-based computing substrate. And yet the vast majority of people are interacting with them the way someone might use a typewriter. One prompt, one response, done. That mental framing is the foundation of everything we will cover today. If you have ever felt like ChatGPT or Claude is not giving you what you really need, the problem is almost never the model. The problem is the interface between your intent and the model's capabilities. And that interface is your mental model of what an LLM actually is. Let's make this concrete. Imagine two people sitting in front of the exact same model, say GPT-4. The average user types me a Python function to parse JSON. They get a function, copy it, and move on. Now watch what an expert like Karpathy does differently. First, they prime the model with role and context. Then they describe the constraints, edge cases, error handling, performance requirements. They ask the model to reason out loud before writing code. They review the output, push back on weak spots, and iterate. The final output isn't just a function, it's a reviewed, tested, explained piece of production quality code. Dramatically different result. This difference isn't luck or access to a special tool. It is entirely a function of how you think about and interact with the model. Now that we have established why the gap exists, let's map out exactly how we are going to close it. This lecture is structured around 5 core pillars that together form a complete framework for Karpathy-style LLM usage. Pillar 1 is the mental model, understanding what an LLM actually is under the hood so your intuitions about it are accurate. Pillar 2 is token thinking, learning to reason about how the model processes information at the token level, which changes how you write prompts. Pillar 3 covers concrete prompting strategies, chain of thought, few-shot examples, role assignment, and more. Pillar 4 is workflow integration, how to embed LLMs into real engineering and research workflows rather than treating them as one-off tools. And Pillar 5 is recognizing and avoiding the most common expert-level mistakes. By the end of this lecture, you will have a systematic, repeatable approach to getting expert-grade output from any frontier model. Before we dive in, let's be clear about who this lecture is designed for and what we assume you already know. This is not an introduction to what ChatGPT is. We assume you have used at least one frontier LLM, GPT-4, GPT-Claude, Gemini, or similar, and you've run into the frustrating ceiling. The model just isn't giving you what you need. Ideally, you have a background in software engineering, machine learning research, or a technical domain where you need the model to help you produce precise, reliable, and sophisticated work. You do not need to know how transformers are trained from scratch, but a basic familiarity with the idea that these models predict tokens will be helpful. If you have that baseline, everything in this lecture will click. And as we move into Chapter 2,
We've covered a lot today, from the query key value paradigm to the full encoder-decoder stack. This architecture is the backbone of ChatGPT, BERT, and Claude. In our next session, we will explore fine-tuning these models for specific tasks. Great job staying focused.